in this video, we're going to start thinking about transient energy balances. So, typically, as we saw in most of this course, energy balances just have the general form of this, as the general form of your favorite sort of equation where you just have some sort of energy accumulation is equal to some input term minus some output term. And so this equation here is fairly simple, right? But typically with transient energy balances, they're fairly complicated because not only are they differential equations, but they're also coupled to the material balance as well. So you have to deal with coupled differential equations. That's outside the scope of this course, and so what I'm going to do in this video is I'm going to derive the energy balance for a very simplified system, so that you just have to focus on one equation at a time. And so for this system, we're going to make a few assumptions. So we're going to work on a closed system so that we don't have to worry about any sort of masses crossing the system boundary. So for this type of system, when we think about our accumulation term, we're going to say it's going to be equal to just the change in the total system energy, delta E sys. Now, as you remember from our energy balances on steady state systems or closed systems when we were looking at the final at the end, if you think about those equations, we're once again on the left hand side, we're just going to be worried about the change in internal energy, the change in kinetic energy, and also the change in potential energy. So the same things that you saw on the left hand side in your other energy balance equations. For the input and the output terms, it's going to be similar to what we saw in the previous chapters, where for input and output we're worrying about things like heat or work. But we're going to write them in a slightly different way. So the way I'm going to write them is for the heat, even though we're working with a closed system, I'm going to write that we're looking at the heating rate, and that's going to be multiplied by some period of time, delta T here. For the work, same sort of thing. We just have some general work term, or general work rate, that's multiplied by some period of time. So now that we define what our accumulation and our input and output terms are, let's put all those things together. So that way, on the left hand side, we have all the changes in the energy. And on the right hand side, we have our input and output terms. So heat rate multiplied by some period of time, and the work rate multiplied by some period of time. I'm then going to divide both sides by delta T. Okay? And when I do that, remember the left-hand side, accumulation, we're saying, is the total change in the system energy. So I'll write it like this. But then I'll write it term by term as well. So it's delta U divided by delta T plus delta EK divided by delta T plus delta EP divided by delta T. And on the right hand side, since we divided by delta T, we're now just left with the heat rate and the work rate. Similar to the transient material balances, the next step I'm going to take is I'm going to start looking at all these delta over delta T terms, but I'm going to say I'm going to start looking at the limit where delta T is very small. It's almost zero. It's infinitesimal. And so what that means is if we take the limit of E cis, or delta E cis over delta dt, that limit is basically the definition of a derivative. And so if we take that same sort of limit and even do it term by term, what we get is du dt plus dek dt plus dep dt, and all that's equal to the stuff on the right hand side. We're now going to simplify this equation even further by looking at the case where the changes in the kinetic energy and the potential energy are negligible. So mathematically, we could say that our d kinetic energy dt and our d potential energy dt, those are basically zero. And so what we're left with is du dt is equal to, well, even before that. So what we're left with is just du dt, right? And so we're going to invoke, what we're looking at here is a total du dt. And what we could say is that that total du dt is equal to some mass times a specific internal energy. Alright? And then for our system, we're also just going to say, to simplify it even further, that the total mass in the system is constant. And since it's a constant, we're just going to pull it out, and we're left with the mass times the derivative of the specific internal energy with respect to t. Let's now take a closer look at the specific internal energy. By definition, if you recall our work in Chapter 8, we could say that the specific internal energy is equal to some reference internal energy, so an internal energy at the reference temperature, plus the integral of a constant volume heat capacity from some reference temperature to the temperature of interest. For the case where our constant volume heat capacity is just a constant, so if CV is a constant, what we could say when we put the specific internal energy into the derivative is that it's going to be the sum of the derivative of this specific internal energy at some reference temperature plus the derivative of CV, and then the integral of a constant is basically a delta t, or t minus the t ref. So once again, for emphasis, I'll just say this is a constant. Alright, and so that's what it looks like when we plug in specific internal energy into our derivative. But of course, this term right here, the reference internal energy, that's a constant, so its derivative is just 0. So what we're left, and also, if we think about this term by term, the derivative for CV times temperature with respect to time, that's just going to give us well, I'll just write it out here. So if we write out the specific internal energy and take the derivative of this term by term, what we get is that we have CV as a constant, and then we have the derivative of temperature with respect to time. And then, when we take the derivative of the part that has a reference temperature, That's a constant. So that's just 0. Alright? And so this is what our du dt term looks like in the end. So if I go to the next page here and put everything back together, what we have in the end is mass times the constant volume heat capacity times dt dt. That's our accumulation term. And that's all equal to just the heat rate plus the work rate. And so that's our general equation. Okay? And so I'll say this is our transient energy balance. But of course, it's not the most general case, right? We had to make a lot of assumptions in order to get here. And so I'll write those out again. So this is a transient energy balance for a non-reactive closed system with a constant CV, and also there's negligible changes in the kinetic and potential energy.